Excellent, please.
So what I'm going to do is I'll give a sketch of our framework for conscious AI, and then Manuel will give more details about our model and discuss frequently asked questions, which there are a number of them. Okay, so let me start. So this is a framework for a conscious AI, and we're looking at consciousness through a theoretical computer science lens. So what is theoretical computer science? It's a branch of mathematics concerned with understanding the underlying principles of computation and complexity, including the implications and surprising consequences of resource limitations. One might say that Alan Turing is the father of theoretical computer science, and in the 30s, Turing and other logicians were interested in answering the question, what's decidable, what's not, what's computable, what's not. And Turing then showed that the halting problem was not decidable. So what the halting problem is really saying is that there's no general purpose program debugger. You cannot write a general purpose program that will look at other programs and their input, and just from looking at it will tell you whether or not that program on that input will halt. And this is actually equivalent to a number of Gödel's theorems as well, but I think the halting problem really fits into the computer science framework. And then for 30 years, logicians were actually working on really categorizing what's decidable, what's not, what's computable, what's not. And in the 60s, with the advent of some large-scale computers, engineers and logicians started to realize that even amongst the computable, even amongst the decidable, even amongst finite problems, some of these problems defied easy solution. So they started asking what's feasibly computable, what's not. And one of these problems is the very famous traveling salesman problem. And that's the problem of you have a number of cities, and you have distances between these cities that you can actually travel. And you have a salesperson who has to go from city A to city B and wants to calculate the shortest path to go from A to B. And of course, it's a decidable question. You could just check out every single path, compute the distances, and then take the shortest one. And unfortunately, this computation grows exponentially with the number of cities, the number of nodes in this graph. And really today, we don't even know a better way to do it. There are some ways to do it in special cases, but we don't know a better way. So this is a finite problem that's really right now not feasibly computable. And then there's the famous P equals NP problem, which you may have heard of. And it's a very interesting philosophical problem because it's basically saying, if you have a problem and you have a solution and you can easily check that solution, well, could you find the solution easily? So think if you have an equation and somebody gives you the solution, you can plug it in and check it out. But is it easy to find it? So that's the question. If you could check easily, can you find it easily? And the answer seems to be no. So there have been a lot of surprising consequences of a lot of these difficult problems. And I think it's the very first time in mathematics when mathematicians have been able to use hard problems to solve other hard problems. So in other words, cryptographically secure pseudorandom sequences have hard problems embedded in them. If you could crack these sequences, then you could solve those hard problems. Okay. The Conscious Turing Machine is inspired by Alan Turing's simple yet powerful model of computation. And here I have a small 23-state universal Turing machine that can compute any computable function. In other words, if you can compute something in the cloud or on a supercomputer, you can compute it on this very simple Turing machine. And in other words, you can get your head around this Turing machine, the universal Turing machine, but it would be very hard to get your head around a supercomputer or the cloud to figure out what is going on. So inspired by Alan Turing, we're looking for simplicity. We're also inspired by Bernard Baars' global workspace theory of consciousness. And Baars describes conscious awareness through a theater analogy. consciousness is the activity of actors in a play performing on a stage of working or short-term memory. The inner speech actor is often on stage, and their performance is under observation by a huge audience of unconscious processors in long-term memory that are sitting in the dark. So maybe this has happened to you once or twice. You're at a party, you see somebody you know, but for the life of you, you can't remember their name. And then you go home and a half hour later, the name pops up into your mind, but it's actually too late. So what's going on? So what's her name gets into short-term memory, and then it gets broadcast down to all the long-term memory processes in that audience. And one of those processes recalls where you first met, maybe in a computer science class, and that goes up to short-term memory, and that gets broadcast down. And then another processor remembers what she does. She studies machine learning or AI, that goes up and then gets broadcast down. And another processor says her name begins with T, and that gets broadcast down. And so a half hour later, her name comes up to the stage from the audience, which has been thinking, searching, and the conscious self on stage doesn't know how or where her name was found. Actually, her name is Sarah, and we'll talk about that. This is sometimes called the Poncare Effect, and Henri Poncare was a famous mathematician who tells this story that he was working on a very hard problem day and night, and he couldn't quite crack it. And he said, luckily, a friend asked him to go on a trip, on a vacation. And then he recalls, as I was about to board a bus, the idea came to me without anything in my former thoughts seeming to have paved the way for it. And when he starts to realize that there are two areas of mathematics, both of which he knows very well, and they seem to be isomorphic. They're isomorphic, they're almost identical theories. And this just popped up into his head. So now what I'd like to do is give you the structure and the dynamics of the conscious Turing machine. But before I do, I want to tell you what it is not. The conscious Turing machine is not a model of the brain. It considers the brain at a very high level of abstraction, well above that of neurons and neuronal activity. So it's in a way above the fray. It's not going to say that this consciousness is happening in the front of the brain or the back of the brain or the brainstem. So we're above the fray here. The CTM is not even a standard Turing machine, because what gives the CTM the feeling of consciousness is not its input-output map, nor its computing power, but what's under the hood. And what's under the hood is a global workspace architecture, but not just that. Plus, it has other features. It has what we call predictive dynamics, and those are cycles of prediction, feedback, and learning. And it has some special key processes, for example, inner speech, inner vision, inner sensation, and especially a model of the world processor that communicate with each other in a rich multimodal language, which we call brainish. So the CTM is defined formally as a 7-tuple, short-term memory, long-term memory, up tree, down tree, links, input, output. And what I'm going to do is describe it through pictures. So here we have a picture of the conscious Turing machine. And up here on top, we have a tiny short-term memory. It's a read-write memory. That's our stage. And that stage can hold one chunk of information. Now, that's not the 7 plus or minus 2 chunks that Miller said was in our short-term memory, but we can get away with one. And since we're looking for simplicity, one will do. Another reason to have just very few chunks up there is we really want to focus. We want this machine to focus on what's consciousness. Okay, so now we have many, many long-term memory processors. That's our audience. These are parallel processors. They're powerful. Each has their own chore to do. And at the beginning, they're not connected. They're not linked at all. And we have inputs coming in through sensors, eyes, ears, nose, from an external world. And that input goes directly to some of the long-term memory processors. And then we have outputs coming from some of the long-term memory processors through actuators to affect the outside world. And at every moment in time, all the processors are putting in chunks into an uptree competition to get their chunks into the short-term memory onto the stage. And once that chunk gets into the short-term memory, it is immediately broadcast by a fast downtree, immediately down to all the long-term memory processors. Now, at the beginning, as I said, these processors are not connected. And the way processors communicate at the beginning with each other is through short-term memory, is through consciousness. But when one processor starts to realize another processor has information that's valuable to it, for example, the processor that asks the query, what's her name? And then another processor said, truthfully, that her name was Sarah, that processor, those processors will link together with a bidirectional link. And as time goes on, more and more of these bidirectional links will form between long-term memory processors. And so processing that would have gone through consciousness at the beginning, more and more of that process will be unconscious. So like when you've learned to ride a bike, at the first, everything's very conscious, but after a while, the process becomes unconscious through the long-term memory processors. Now, these processors, each processor has their own language. For example, the inner speech processor might have a language which somehow mimics outer speech, but to communicate with each other in the CTM, there is an inner language called Brainish, and it's a rich multimodal language. And this language is richer than, let's say, an outside language. It's more than just words. It's images, sounds, sensations, smells. So that's our Brainish multimodal language. So now I've given you a little sense of the short-term memory, long-term memory processors, uptree, downtree broadcast, links between processors, inputs coming from the external world, outputs going to the external world. But I'd like to now focus a little bit more on the uptree competition. So the uptree competition is conducted by a binary uptree. And so let me give you a little bit more information. As I said before, at each moment in time, each long-term memory processor puts a chunk into the competition. And let me formally tell you what a chunk is. So a chunk is a six-tuple. And a chunk is a processor P will put a chunk into the competition. And the first parameter of the six-tuple is the address of the processor. And we're making an assumption there might be like 10 to the 7th processors, maybe mimicking the 10 to the 7 cortical columns in the brain. So an address could be like a 7-digit number, the log of that address. So we have a 7-digit number here for the address. Then T is the time the chunk was put into the competition. And weight is the importance or the value or the confidence that the processor has in its chunk. And I really missed the very key thing here is the gist. And the gist is really the succinct bit of information that the processor really wants to convey, like what's her name, or her name begins with T, or her name is Sarah, or whatever. Okay, so that gist is a succinct information in Brainish that's in this chunk. And again, the weight is the importance that the processor gives its information. And then we have two parameters here that I have in green. One is the intensity, which starts off as the absolute value of the weight, and the other is the mood, which starts off as the weight. And as the processor, these processors put chunks into the competition, and as these chunks, they're going to compete locally, and as they move up the competition tree, the first 4 parameters will stay the same. The address, the time, the gist, and the weight will stay the same. But the intensity and the mood will differ, will change as it's moving up. So let me tell you a little bit more in detail about what's going on. So at each node in our uptree, we have what we call a coin flip neuron. And what this coin flip neuron does, it takes two non-negative numbers, A and B, and it computes A over A plus B, and that calls that the probability of A. And then the probability of B is called 1 minus the probability of A. So what we've done right now is we've now converted a deterministic system into a probabilistic conscious Turing machine. And from now on, I'm going to just stick with the probabilistic conscious Turing machine. And there are many reasons to do this, one of which it makes life much easier. Okay, so now I'm going to tell you how if we have two chunks that have moved up to these nodes, C1 and C2, how do we decide on the probability of the winning chunk there and what's the new chunk moving up? So we have a general competition function. So f of chunk is the intensity, the current intensity of that chunk at that stage, plus C times the mood, the current mood, where C is between -1 and +1. And let's just for the moment think of C as 0. So f of chunk is just the intensity, the current intensity. And now let's suppose f of C1, the chunk on the left here, is greater than f of C2. Then with the probability f of C1 over f of C1 plus f of C2, C1 will be the local winner. And with that probability, the chunk that moves up will look like C1 for the first 4 components. They will have the same processor that put it in, the same time it went on, the same gist, the same weight the processor gave. But the last 2 components will now have changed. And what we'll have there is the new current intensity will be the sum of the C1 and intensity of C1 and the intensity of C2. And the current mood will be the current mood of C1 and the current mood of C2. And then with this competition function, which has a very nice properties, it's called an additive competition function. What we can show is that the probability of a chunk winning the competition, so this chunk that was put in at the initial stage, will be f of that C over the sum of f of all the initial f of each of the initial chunks that were put into the competition. And that has a very, very nice property that the probability of a chunk winning is independent of the location of the processor that put the chunk in. So even if we have this binary tree, it really doesn't matter where those processors are located. Okay, I'd like to say a little bit more now about what's in some of the long-term memory processors. And each long-term memory processor, excuse me, has one of Avram Blum's sleeping experts algorithms in it. And what these sleeping experts algorithms do is they tend to modulate the weight that each processor gives its chunk. So for example, remember there was a processor that said her name began with T, but actually it turned out her name was Sarah. So what that sleeping expert will do is tell that processor, hey, you better lower your weights. You're getting into short-term memory, but you're a little too egotistical, lower your weight. And then maybe some processor originally said her name was Sarah, but that processor, though correct, didn't give enough weight to Sarah, so didn't get into short-term memory right away. So the sleeping expert algorithm, when it finds out her name was Sarah, will tell that processor, okay, raise your weights. So in other words, the sleeping expert algorithm will embolden its processor if its chunk did not get into the short-term memory, but its information is more valuable than what did get into STM. On the other hand, as the sleeping expert's algorithm will hush the processor if its chunk got into the short-term memory, but the information in that chunk is found to be less valuable than of another chunk that failed to get into STM. And this can be done very mathematically, but this is the key idea. Okay, so we're now starting to see some simple, what we call predictive dynamics in this machine, cycles of prediction, feedback, and learning. So what are predictions? When the processors put chunks into the up tree competition, that's some prediction of theirs. When a processor will send a chunk to the actuators to go to the outside world, the external world, that's a prediction. So what's a feedback? A feedback could come from the outside world through the input map. The feedback could come from the short-term memory through broadcast, and which all the processors get, and they know which processor won the competition. So based on that, that processor that processor will use the sleeping expert's algorithm, the learning algorithm. So here we have prediction, feedback, and learning within the processors themselves. Okay, so now I'm going to give some definitions. The conscious content of the conscious Turing machine at a time t will be the chunk that's in short-term memory, or in other words, the winner of the uptree chunk competition at that time. And then we'll say conscious awareness or attention is the reception of the broadcast of the conscious content by all long-term memory processors, and the subsequent chatter amongst the long-term memory processors via links, and we call this ignition, which sort of mimics a little bit of Dehaene and Changeux's theory, the global neuronal workspace theory. And then the stream of consciousness will say it's the time-ordered chunks that are broadcast from short-term memory into long-term memory. So there's this constant bubbling of activity, and the time-ordered chunks that are broadcast, we'll call that the stream of consciousness. But these are definitions, and the reasonableness of our definitions, of course, will come from the number of concepts that the model explains easily and naturally. And at a high level, we're able to consider some phenomena that's generally associated with consciousness: pain, pleasure, dreams, free will. And I'm going to look at three things: blind sight, inattentional, and inattentional blindness and change blindness, and see how the CTM can give at least a high level explanation that is consistent with some of the cognitive neuroscientist literature. So we're going to start with blind sight. And here we have a gentleman sitting on the right, and he's in this very cluttered living room. It looks like an obstacle course. And he's asked to go to the other room. Perhaps there's food being served there. But the man says, but I can't see. Nevertheless, he gets up, walks to the door, avoiding the obstacles. So what's going on? So let me give you a high-level explanation from the Conscious Turing Machine. So we have input coming from the external world, like from the eye, and that's going directly to the vision processor, which works properly, and it sends its message to the walk actuator, and so the guy can walk across the room. But the connection from the vision processor to short-term memory is broken. So that information never gets into short-term memory consciousness and never gets broadcast down. So without the vision processing having access to short-term memory, this gentleman has no conscious sense that he can see. And at a high level, this explanation is consistent with explanations of blind sight giving in the literature. Okay, now let me look at unintentional blindness in the Conscious Turing Machine. And I think many of you have seen this film before. And viewers are asked to count how many times white-shirted players pass the ball. And I think it's about 15 times, and most people get it right. But did you see the gorilla? And most people did not, even though the gorilla is there in plain sight. So did the CTM, our Conscious Turing Machine, see the gorilla? It didn't either. So what's going on here? So when this Conscious Turing Machine is given a task, its processors give higher weight to the task. In this case, it's looking for white. And it won't be conscious of other things that are given lower weights, like black. Those chunks will never get into short-term. We'll have a very low probability in our probabilistic Turing machine of getting into short-term memory. And again, the effect of differential intensities in the conscious Turing machine is consistent with implications that the intentional blindness in humans can serve as a filter for irrelevant information. It may also serve as a filter to filter out unexpected events. There are other explanations, but that are different but consistent with these explanations. And now finally, I'll look at Chane's blindness. And again, this famous whodunit film, and this detective comes into a room and he sees this dead guy on the floor, and he says, clearly somebody in the room murdered Lord Smythe. Each of you tell me your whereabouts. And the maid says, I was polishing the brass in the master bedroom. And the butler says, I was buttering his lordship's scones. And Lady Smythe says, I was planting my petunias in the potting shed. And the clever detective immediately says, Constable, arrest Lady Smythe. And that's a puzzle to us, how he got that so quickly. But a bigger puzzle is, how come we did not notice all the changes from the first scene to the last scene? So here you can see the detective's coat was dark before, now it's light. And the flowers have changed, but even the dead guy has changed his clothes, and now his leg is up in the air. So what's going on? Why didn't the conscious Turing machine, why didn't we see the many changes? And here's again our explanation in this conscious Turing machine. Detecting change in the whodunit video would have required changes in GIST describing the beginning and ending scenes, but size limitations on the conscious content. So we said the GISTs are succinct information, they're the GISTs of what's going on, and the clever scene transition cause the high-level descriptions to be essentially the same. So the same gist describes the first scene and the last scene. The scene is a living room of a mansion with a butler, maid, and detective, and the man laid out on the floor. That's the same gist for both, describing both. The CTM explanation, again, is consistent with literature on change blindness. Okay. So now I'd like to ask, why would a robot with a conscious Turing machine feel that it is conscious? So here's the conscious Turing machine. And now I need to look at some special long-term memory processors. So one of the processors is an inner speech processor, which allows our conscious Turing machine to talk to itself in some language which may mimic its external language. And it also has other processors that are really important here, like the inner vision, inner sensation processors. But I'd like to concentrate on the model of the world processor. And the model of the world processor is actually it's a large collection of processors, and they're tasked with making models of CTMs, the conscious Turing machine's inner and outer world. And so let's look at the conscious Turing machine from the point of view of the model of the world processor. And so the model of the processor tags elements in its various models of the world in succinct brainish gists. Here we have some labeling, including labeling sensors and actuators as self when it consistently detects them carrying out conscious requests. And also it labels unself or not self, those that are not part of self as well. Looking at the CTM from the viewpoint of the outside world, we see something about the CTM is conscious. Specifically, the CTM considers itself conscious, but what is conscious cannot be the model of the world processor or any other processors, as processors have no feeling. They are just machines running algorithms. So we propose the view that the CTM, the conscious Turing machine as a whole, feels conscious as normally understood, is a consequence and part of the fact that the model of the world processors views the CTM and its model of world as conscious, and that view is broadcast to all processors. And this is kindred in spirit to Michael Graziano's attention schema theory. So now let me recap. Key features of the conscious Turing machine for a conscious AI is first the global workspace architecture. or the global broadcast, predictive dynamics, cycles of prediction, feedback, and learning, certain special long-term memory processors, inner speech, inner sensation, inner vision, the model of a world processor that communicate in a rich multimodal language, brainish, and also our particular attention to resource limitations, both with respect to construction and with our explanations. And these explanations come up in consciousness and also in feel that our conscious Turing machine will feel it also has free will. So now I'd like to thank you, and a really great appreciation to Hiro and Ryota and the Consciousness Club of Tokyo for your invitation to present our research. And we also like to appreciate our friend Michael Schwann for his encouragement, and to Unidata Technologies for helping support this research. And now we're going to go on to, let's see if I don't have this slide here, to Manuel, who's going to give us a few more details about the Conscious Turing Machine, and also frequently asked questions. He's going to discuss frequently asked questions. So Manuel, now it's all yours. And I think I can stop and you can share your screen. Okay, all yours.
Can you hear me?
I can hear you. Yeah. Can everybody else?
Good. Yes. You want to ask if people have questions for you?
Well, let me go ahead and we're going to address them. So we're going to tell more of the frequently asked questions, and some of those will come up. So why don't you go ahead?
Yes. Can I ask just one question?
Sure. Sure. Go ahead. Who are you?
Sorry, my name is Takashi Kegami. I'm from the University of Tokyo. Sure. What I'm doing is artificial life and the complex system sciences in general. My question, my question is very simple. When you think that the Turing machines using a Turing machine as a consciousness model, or make a Turing machine conscious, the big problem to me is how do you accept this halting state? So without the halting state, Turing machine just becomes dynamic systems, right? Or the cellular automata. So I really want to understand what's the halting state meaning to consciousness.
Right, so this is not, as I said, this is actually not a Turing machine, and we call it a Turing machine because we're inspired by the simplicity of the Turing machine. So this is not at all a Turing machine. It could be a Turing machine, but if it's, so a lot of people have asked, and I think Manuel will address this, suppose if this is a Turing machine, why is the Turing machine conscious? And we'll argue that, I'll let Manuel talk about that a little bit, but we'll argue that the input-output map is not what makes the machine conscious. It's having all of these features. It's having all these features. So we're not claiming this is a Turing machine. We're only inspired by that.
Why I ask this question is because sometimes there's an aha moment that, the same input, but at a certain moment that we got a aha moment that you just, I got it, right? I mean, this kind of moment.
Yeah, and that's our conscious Turing machine will have these aha moments as well. It will play chess and it will look at different possibilities and it will have an aha moment. Like, this is the move I'm going to make. Yes. And it's going to have the free will to do that. It's going to feel it has free will, but it does have resource limitations. There's time in it. It's a finite lifetime. And that's our machine does have those resource limitations. And that's, and in fact, that's critical to many of the explanations of consciousness is the size, the resources limitations, both into the size of this, the amount of time we have to make decisions, though within our time, we're perfectly free to make whatever decisions, make any computations we like. I think I don't want to go on. So let's come back to this at the end.
Okay, yeah.
Because this is one of the frequently asked questions that we have, about 25 of them or 30 or whatever.
I see.
Okay.
Thank you very much.
So, thank you, thank you, and we'll discuss more. Manuel.
Okay, let's see. Can you see my screen?
We can see it.
Okay, so I'm just going to keep on going. I like Takashi's question, and hopefully we'll get to it here. And probably I won't answer it very well, but I'll try. So let me start with this. Baars' global theater model, I think, is a great idea. But it leaves us with a lot of questions. And what I'd like to do is look at one of the many questions that comes up. And that is the question of how do processors decide what information should get to the stage? So when Baars describes his model, you have this huge audience, and he talks about the audience members in getting together to decide what should go up to the stage. But it doesn't say how they get together and what gets up there. So how in fact does that happen? And I'm going to go into some detail on how that happens, or how that can happen, how that happens in the CTM. So one idea here is to look at chess and tennis tournaments where the goal is to crown the strongest player, right? You have all these tennis players, who's the best player? And we're going to say, suppose the player, in the case of the CTM, the players are these processors. Suppose the players have weights W1 through Wn. This is the weights that they assign to the information that they have available. Just what these weights are is kind of interesting. It reminds me of weather predictions. You know how they say that the chance of rain is 30%, and you wonder, does that mean that it will rain, but there will be 30% as strong as the maximum possible? Or does that mean 30% of the time it will rain? Or does that mean, well, I'm not sure, but maybe, anyway, there are many meanings. The same thing is true here. These processors have weights, and the sleeping expert really, algorithm really says how those weights are adjusted to come to some reasonable meaning. The meaning of these weights in this CTM theory is that if processor I and processor J play against each other, then the probability that processor I beats processor J is Wi divided by Wi plus Wj. Okay, so you can imagine if these are tennis players, they have weights. If they are chess players, they have also weights, and this would be the meaning of those weights. We'll say a tournament is fair if the probability that processor I wins is given by its weight divided by the sum of all weights. Lenore mentioned this. It's basically saying that the probability that the processor I wins is proportional to its weight. So what I'm going to do now is say that that chess and tennis have a way of setting up the tournaments so that they try to make sure that they try to approximate a reasonable probability of a processor winning, a reasonable fair probability. I'm going to show you how they work, and then I'm going to show you how the CTM works, which is rather different and has a nice property that the tournament is fair. So let me show you how this is done here. I'll start with, I'm trying to get I have the pictures of everybody here right in front of my eye. I have to get it off to the side somewhere. Okay. Okay, so let me show you how the standard way in which we consider, which is unfair, but standard way in which one chooses who's the winner. It would be a tennis or chess or whatever. The standard way is you have these weights, and here are four processors, A, B, C, D, and they have weights 3, 1, 4, 1. And to decide who wins, well, it's a probabilistic decision. So let's look at the probability that A will actually win. And the way this works is the weight of A is 3, the weight of B is 1. When A plays B, the probability that it wins is 3 divided by 3 plus 1, which is 3/4. Okay, 3 over 3 plus 1 is 3/4. That's the probability that A wins that first match. The probability that A then goes on to win the next match, it goes like this. It's 3/4. That's the probability. A wins this particular tournament if it won the first match, which it wins with probability 3/4, and then it wins against C and D. And the probability that the probability that C won is 4 divided by 4 plus 1 is 5, is 4/5. But Lenore, do you see the arrow that I'm moving around here?
Yes, I do.
Yeah, okay,
Yes.
good. That's the 4/5 is the probability that C wins. And then the probability that A, that has weight 3, beats C, that has weight 4, will be 3 divided by 3 plus 4, which is 7. Add to that now the probability that D wins, which is 1/5, and the probability that A beats D, which is 3/4, and you come out with a value which is 0.37. This is the way chess and tennis actually work. That's the standard way for a tournament. You'll notice that points, okay. I want to make the point that this 0.37 is not quite what we want. In a fair game, the probability that W should win would be 3 divided by the sum of 3 plus 1 plus 4 plus 1, which is 9. So the probability that A wins should be 3/9 or a third, which is 0.33. So this is not quite right, but close. Okay, let's go on to the way we do it in the CTM. So I think Lenore already mentioned this. The way we do it has a nice property that, first of all, it will be fair. The A will really win with probability 1/3. And the way it works is that A will play against, so there's the probabilities. It will be fair. It will be fair in the sense that when we're done here, A will have a probability exactly 3/9 of winning. And the same will be true for B having probability exactly 1/9, and so on. So of course, this tournament is a bit different from the standard one. And what's different is that we're using not the weight, but the intensity. The intensity starts off being the weight. So initially, the probability that A wins at the first round is indeed 3 divided by 3 plus 4, 3/4. That's the probability that A wins the first round. But whoever wins, whether it's A or B, they go up to the next level with the same weight, but their intensity becomes the sum. The 3 plus 1 is 4, is the actual intensity that the winner takes up to the next level. And the same thing is true over here with C and D. Their intensities are 4 and 1, but when the winner gets up to the next level, its intensity will be 4 plus 1. That's 5. And now, at the next level, the decision the probability of A getting up to the next level. So it got up to the first level is probability 3/4. The probability that it gets up to the next level is given by its intensity 4 divided by the sum of the intensities 4 plus 5, which is 9. So probability of A getting up to the next level is 3/4 times 4/9, which is 3/9, which is 0.33. That's what you want. That is fair. Okay. there's something interesting going on here. The 3/4 and the 4/9, the 4s cancel to give you that 1/3. So this is important for the proof that this is always going to work. Okay, let's look at another example. Again, okay, good. This is a okay, so we're going to have here, I have the pictures of the people in the audience, and so I have to move these pictures around. Sorry about that. Anyway, so let's look at a slightly bigger tournament. Again, red will be the standard tournament. Computations are in red. They use the weight, not intensity. That's the way it's done. And this would be the case of the chunk. We're simply given by the processor address, the time, the gist, and the weight. And then we'll see the CTM tournament computations will be in blue. Those are the computations that make use of the intensity, or the most general intensity plus a constant times the mood. Okay, so let's
people out of the way.
okay. Well, Lenore is here to help me. I did move it over, but then
Yeah, okay.
I did do that. That's always there somewhere.
Okay.
So, okay, yeah, right. It's okay. So anyway, let's see what happens in the CTM computation tournament. So, well, let's first of all see what happens with the standard. The standard one you already saw. Let me just say that the weights here, I'm playing with 8 processors. For random numbers, I always love pi. So 3.1415926. See, it's I'm using pi for the weights over here. And the way the standard computation would go at the start, probability that A wins is 3 divided by 3 plus 1 is 4. That's 3/4. At the next level, you can compute the probability as we did before, and the probability turns out to be this 0.37, essentially 0.37. And then at the next level, the probability of A, I'm just looking at the probability of A getting there. The probability of A getting to the top is given by the probability it gets to the first level, and then the probability that gets to the second level, and then we compute the probability that it gets to the last level, and that will be 0.3122. 0.3 basically. Okay. Now let's look at how the CTM does this. Here we're claiming, we don't have to go through those computations, we're claiming that each processor will win with probability proportional to its weight or intensity at the start. So if A has weight 3, the sum of these digits is 31. A will win with probability proportional to its weight, which is 3 divided by 31. Probability that B will win will be 1 divided by 31, and so on. And the computation which we'll do, which sort of shows you how the proof actually then goes, is these 2 processors take their weights and add them to get the see, the weights are the intensity at the start, but at the next level, the weight stays the same, but the intensity is the sum. It doesn't matter whether A wins or B wins, the intensity at the next level will be 4. And so the probability that A will get to that next level will be still 3/4, but the probability that we'll then get to the next level above that will be 4 divided by 4 plus 5, or 9. Sorry. Probability that we'll get up to the next level will be 4 divided by 4 plus 5, which is 4 divided by 9, which is 4/9. So here's the probability that A gets to that second level is 4/9. the probability that it then gets up to the final level will be 9 divided by 9 plus 22, which is 31. And here you see the 4s cancel, the 9s cancel, and you're left with 331, which is exactly the probability that A should get to the top. We can put this slightly different form here. The probability that A gets to the top is 3/4 times 4/9 times 9/31. You see how the 4s cancel, so that you can see why you get 331. It's very simple. Nothing difficult here, but you get the right probability. A really gets to the top with probability, which is roughly 0.1, whereas the standard method gave you a probability of 0.3, which is rather wrong. Okay, it's 3 times as much as it should be. So the standard method does not work very well. In chess, and let me explain something about this. In chess and tennis, this difficulty arises because you have, as in this case, the strong players are on the right and the weak players are on the left. So no matter what, a relatively weak player is going to get at least up to, but very close to the top. And so it has a rather better chance to win than you might expect. The chances of winning, of A winning, is rather higher, and the chances of 9 winning, of F winning, is going to be lower than what it should be. Okay, why am I going into all this detail? First, because I do want the tournament to be fair, course, but there's another reason, and that is that this argument now is independent of where A, B, C, D through H are located. They can be moved around, they can be permuted. In chess and tennis, one starts by putting a strong player like 9 on the right and a weak player on the left. Take that back. You start by putting the strongest player on the right tree, and then the second strongest player on the left, and then the third strongest on the right, and the fourth strongest on the left, back and forth. So players are moved around in order to ensure that there's a reasonable chance that the strongest player, which is on the right, will play against the second strongest player on the left. That doesn't happen here because the strongest and the second strongest are 9 and are F and H, and only one of them can get up to this second level. So the point I'm trying to make here is that the process, that not only is this way of doing the computation via intensity fair, but also processors can be moved around, and it will not affect the probability that a processor like A gets to the top. It will not matter. Isn't that wonderful? You can permute them any place you want, and the same processor will get its chunk up to the top with the same probability. So that's so let's see. So it's now 10 o'clock. Hiro, I have frequently asked questions. Shall I keep on going, or have you had enough of this now?
Right.
How much time?
I think we have like 10 minutes. Then like we can maybe take a little bit short break.
Sure. Sounds good.
So
why don't I just do this? I'll mention that there are 28 questions altogether.
yeah.
Some of these were asked by people who were, some of these are really questions that were asked by reviewers, and some of them are questions that we came up with, which we thought are good questions to have. So, like the first question, will be, since the universal Turing machine can simulate the CTM, won't it also be conscious? And we say that no, and I'm hoping that this is answering one of the questions that was asked before. But anyway, there are 28 questions. We'll get back to these. Why don't we stop for the moment, okay?
Mhm.
Hero.
Yes, so I think why not putting some of the like maybe very key questions, and like we can stop and then have a short break for like 5 minutes. Is that fine? Maybe like some people wants to think about based on the questions or
So what would you like me to do?
so yeah, I want you to show some of the key questions, and like we can stop and have a short break. What about that?
Yeah, why don't you give a few questions, go through a few of the questions, Manuel, and then
Okay,
we'll
okay, sure, okay. So
And
there are
nice.
28 questions altogether. Let's just go through a few of these. The first question is, since a universal Turing machine can simulate the CTM, won't it also be conscious? So that's a good question. I think that was the question that maybe that was asked us, that was asked Lenore. The point here is that, yes, the Turing machine can simulate the CTM as a Turing machine, but not as a conscious Turing machine. The definition of consciousness requires that what's in short-term memory is broadcast to all processors, and all processors receive that information at exactly the same time. In the universal Turing machine simulation, the processors are getting that information one at a time. It's not simultaneous. So when you look at it, it's just not simulating the conscious Turing machine as a conscious Turing machine. Another question, since the CTM has free will, won't the universal Turing machine simulating the CTM also have free will? It's interesting because we don't see the CTM as having free will. Let me just mention that there was this man who lived around the same time as Newton. His name was Samuel Johnson, and he had something very interesting to say about free will. He had these very clean, short quips, and his statement about free will is, all science is against the freedom of the will. He knew about Newton. He knew that everything is determined. All science is against the freedom of the will. All experience is for it. I love that quote. I love it because, in fact, let me just say that I don't believe that we really have free will. Everything is determined, but we certainly have the feeling that we have free will. And I would explain this sort of in terms of a chess. Imagine that you're playing chess, and it's your turn. You have to make a move. You can move the bishop here or the knight there. You have one of two moves. The others are not very important. Which one will you do? It is determined which one you will do, but you don't know what you will do because you haven't actually done the computation. What you know is that you will do some computation to decide which move you will make. You don't know yet which, even if it's determined, you don't know yet what the result of those computations will be, and therefore what you will do. So you don't really have free will, but you do have the feeling that you have free will because you know that you will compute as best you can and then go with whatever move is in your best interest. Is the CTM a blueprint for conscious AI? It's a framework. It's not a blueprint. What advantage does the CTM architecture offer? Well, certainly an important advantage is that if you don't know where the information is stored, you can ask, you can broadcast, what's her name? And wherever it's stored, you hope you'll find out what the name is. So the important and an important advantage, there are others, an important advantage is that when you don't know where information is stored, you can get all the processors looking into it for you. Why does the STM hold only one chunk? Yes, because we can get away with one chunk. I'll just mention here, I'm going to go through these 8 questions and then we'll break. So why does the short-term memory hold only one chunk? So of course, one chunk is less than 7 plus or minus 2, less than George Miller's 7 plus or minus 2. I think when people first hear about that 7 plus or minus 2 chunks in short-term memory, it occurs to them, how can you get by with so little information in short-term memory? It seems like you need a lot more, that you're actually aware of a lot more. It's kind of nice that you can get by with just one chunk. And to show how this works, the appendix to our archive paper, the second archive paper, actually has some examples of how this is done. One of the examples is how the CTM goes about living its life in the morning, when it wakes up, what goes on in the CTM. Another example is the second appendix example is, how does the CTM recall the proof of a theorem, in this case, the theorem that the square root of 2 is irrational? How does the CTM go about recalling that? And with only one chunk in short-term memory at a time, you can see going through the process of recalling that proof. And the third appendix says, how does the CTM go about finding new theorems? How does it go about extending that proof that square root of 2 is irrational in new directions? And I think that those are the only 3 we have, but they go part of the way to giving you an idea how it gets by very naturally with just one chunk. Why is the CTM defined in the specific format given? It's okay, there could be others. What distinguishes conscious STM and unconscious LTM processors? You know, consciousness is what goes up through short-term memory, links form, and then what was done consciously initially becomes done unconsciously. I sort of like the fact that when you learn ping pong, you know that if you're going to play ping pong, you have to pay attention. You are paying conscious attention to how you play. But links do form, and the ping pong players who are really good at this say that when you're in a tournament, you turn off your consciousness, you let your hand do whatever it wants to do. It works unconsciously. And why is the up tree a strictly binary tree? It doesn't have to be. It could be a k-ary tree for some small k. The important thing is that for some small k, the number of steps to get from for a chunk to get from the processors, the long-term memory processors up to short-term memory is still going to be log of the number of processors. Can't get away from that. Maybe the base will change. With a binary tree, it's log base 2 of the number of processors. With k, it would be log to the base k of the number of processors. But so does it have to be strictly binary? We make it binary just because it's the simplest thing to do, and we can explain, and we want simple. Okay.
Right. Yeah. Thanks a lot. I think a little bit. We already passed 1 hour 5. So why not having a 5 minutes break and come back now in Japan 11, maybe 15. We will start.
Sure. Sure.
Yeah. Okay.
If anybody has any questions, I'm here. They can still ask.
Thank you.
Let me ask just because probably I have to go. First of all, I studied the lecture book by Ms. Blum. So when I was a graduate student, so I'm very much happy to be here at your presentation. And so my question is, do you think discrete systems is still okay for understanding consciousness? Because some people say that the real numbers are necessary. That's what I think you guys try to propose, that the real numbers are necessary for understanding consciousness state. And then I think, for example, Roger Penrose was also saying that the quantum entanglement is important because it's a non-local operational system. It is important for the consciousness system to emerge. So if you have any, I mean, maybe there's one of those FAQ, but if you have any comments on that, that would be great to hear that.
About the quantum.
Yeah, I mean, do you need a real number to?
Yeah. Our weights are real numbers.
Yeah.
They're not integers or digits. They are real numbers. We're allowing real numbers. We want it to be as simple as possible, and we find it easier to have real numbers and not worry. They're not even floating. Maybe they're approximated by floating point numbers, but we don't want to have to worry about size of the numbers or the values. We want, when the sleeping expert has to decide whether to perhaps double the weight or half the weight, has to decide what to do with weights. We don't want to have to worry about whether the numbers we're getting to are allowed or not. So we just have real numbers.
So I'd like to say about real numbers. So we have a model of real number computation, and this does actually, most of machine learning falls within, most of machine learning uses real numbers. And there is a formal theory of real number computation, which I developed along with Steve Smale and Mike Shub, which is analogous to the Turing model. So you would say that maybe our conscious Turing machine is really a little bit of a hybrid, because we are using real numbers, but we also have a very formal theory of real number computation, which fits in fine. So actually the Turing model is an example of our general model of computation. It's just that the Turing model is the field you're looking at, of the reals are Z2 rather than R. So we do computation over any ring, and the ring could be the real numbers, the complex numbers Z2 or whatever. So we have a general theory that this fits into. But that's an interesting question. And I think your question about, quantum entanglements, and there is this feeling that quantum may come into consciousness. I think even physicists like Sean Carroll, who will disagree with that. I mean, there is a group that feels quantum entanglement and quantum collapse is fundamental, but I think there's a whole group which are part of, which looks at more classical physics. Would you say that, Manuel?
I agree that we don't need quantum collapse. Yeah, so there's nothing like that in this CTM theory. We don't require it. We don't want it to be an explanation for our feelings, consciousness, pain, stuff like that.
Okay. Thank you very much.
Yeah, and also I should say that all of the complexity theory that's done on finite, really one is not looking for halting problem there at all. When you're looking at like the traveling salesman problem or other difficult problems, things like halting does not come in. What comes in is, rather than decidable, undecidable, it's really polynomial versus exponential is the dichotomy at that point. And that, I think that also influences what we do too, is that if it's not feasible, it's not going to happen.
Okay.
Good. Yeah. Thank you.
There. Yeah. But interesting. Can you just tell us a little bit about what you're at the University of Tokyo, and you said your interest is?
Yeah. Actually, I'm doing artificial life, and then try to make living systems from non-DNA, non-cellular systems, and then
organoids. Is that it? Is it Conway's artificial life or organoids?
Well, Conway is one of this. He's the founder of artificial life. So when so we invited him as a keynote at one of those A-Life conference, and then he said, we are all wrong because we are using either stochastic equations or deterministic cellular automata or dynamical systems. And he said non-deterministic rules are necessary to understand living systems. So that's our argument started. And then I was wondering, whether
could you just repeat that again? He said what is not important or what's important?
He said that non-determinism is important.
Right. That's what he said. He said
non-determinism meaning.
Non-deterministic means the non-stochastic, non-deterministic. I mean, it's the state here. It doesn't affect the future, but it's you cannot. It's completely unpredictable. That's what I think. That's what he meant. So
it is true that in quantum physics, it's interesting that in quantum physics, the rules are calculable. It's when samples are chosen, they're chosen with a specific probability, and so the rules themselves are completely deterministic. Even though the choice of a sample, for example, is random.
Yeah.
And one of the things that comes out of this CTM is that. Whether it's the quantum physics or completely deterministic physics, our definitions of consciousness, of chunk, all these definitions still hold, and we argue that the machines will feel conscious, will feel that they have free will, whether there is quantum physics or completely deterministic physics, as in the game of life.
I think his point was that a causal relationship doesn't help us to understand conscious state, but we have to think something else, like just a correlation between this state and another state. But there is no something like, this causes this to happen. And that cannot be the underlying conscious state that we can make. That's what I think he also tried to say.
Okay, we'll take this offline.
All right, yes.
Very interesting, yeah.
Thank you for that.
No, my great pleasure. As I said, the book. The real number complexity book was one of my Bibles, so thank you so much.
That's my book. Yeah. So usually people know Manuel's work more than mine, so nice. There's somebody with a hand up, but I don't know. Oh yeah, you have your hand up there.
Yeah, please.
Nicholas
Takashi.
Gutenberg?
Yeah, I think Takashi was first. Please.
Yeah.
May I ask very short, simple questions? 3 questions.
Sure.
First question. So, consciousness is an emergent property. I think that the consciousness emerges from the complex behaviors. That is a basic assumption. This is my first question. So
I'm not. I see you got you put something into the chat.
No. I don't have chat.
No. So Nick, is that Nicholas talking?
Gunther.
Or Takashi?
Yes.
Higami-san, who put that in the chat.
Okay. Yeah, so
I didn't understand the question.
There are many people think that when when things become complex enough, a consciousness will emerge, and I think that's not our view. We're just saying that there are some fundamental principles. Maybe they're different ones, but we're saying that with these fundamental principles, you will have a machine that feels it is conscious, that feels it has free will. So that's what we're claiming, that if you have some of these simple, at least the framework, we're not giving the details of how, of course, a model of world is going to be very complex of how this machine is going to make, really good models of the world. That has to be done. But with this framework, we're saying that this machine will feel that it's conscious and it will feel it has free will. And it doesn't have to be more complex for that to emerge.
Good.
Okay, thank you. That was my question. The second question is you said architecture is very important. So if we don't know the architecture, we cannot judge this has a consciousness or not. So we need to know architecture to decide to discuss on the consciousness.
I'm sorry, Lenore? I didn't understand.
Yeah, I didn't.
So my second question is I think you explain the consciousness Turing machine. So what is long-term memory and short-time memory? So this kind of architecture is important, something like that. So my question is that in order to judge, or in order to decide the consciousness, in order to discuss consciousness, we need to definitely know the architecture of the system. Is it right?
So I think the question that you're asking is, how can you tell, how can you tell if a machine is conscious? Is that sort of what you're getting at?
Yes, so, and in order to discuss the consciousness, we need to definitely know the architecture. Architecture is very important. That
I agree, yes.
So we're claiming yes. Though we're
giving an architecture which we think will lead to consciousness, but we're not claiming that that's the only architecture.
Mm-hmm.
Tononi, of course, has this idea of what might lead to consciousness. It's much more general. We're not, ours is not that general. We're just saying for this particular architecture, we're arguing that this thing will be conscious.
Okay.
We'll feel it's conscious.
Okay.
We're not saying it's unique or in any way. But also, in terms of computation, Turing had his Turing machine, which was one model of computation. And it turned out that there were many different, very different looking. There were equational models. There's lambda calculus, many different models that had the same fundamental underlying computable functions, though the models look totally different. So we're not claiming that this is unique at all. On the other hand, it does have features that are consistent with others. So for example, the model of our model of the world explanation is very consistent with attention schema theory of Michael Graziano's, who's a neuroscientist. Of course, we were influenced. We didn't know about that actually when we had our model of the world. We found out about his work later on. But on the other hand, we were influenced by the global workspace of Baars and the global neuronal workspace of Dehaene and Changeux. So we are basing the model on some cognitive neuroscience, that's true. We added other features, which it turns out that also are features that cognitive neuroscientists have as well. So we're feeling pretty confident in constructing that one could, at least we're giving a framework. It needs a lot of blueprint details to work out. A really interesting thing is, Alan Turing gave this very simple model of computation in about, I think it was 1932 or 3 or so. But in 1945, when he went to the National Laboratory in England, he came with a 50-page complete description of a universal computer, that programmable computer, and he had all the details. He had the programming languages, he had the chemistry, he had everything, he had the circuit diagrams. So he actually did come with, so you might say the Turing machine is the framework, but he actually came with the blueprint. And became known about 10 years ago, 10 or 12 years ago, that he
We, on the other hand, don't have a blueprint.
We don't have a blueprint. We're hoping students and others, I see Michael Schwan is on this Zoom, and Michael Schwan has some of his colleagues working on this. We have a student at Carnegie Mellon, so of course we've talked about Brainish. Paul Yang is a graduate student at Carnegie Mellon who's an expert in multimodal machine learning, and he's developing a syntax and semantics for a Brainish. So we're hoping that students and others will develop the different components, blueprints at least for the components that we're saying. And I know that Ryota has, there's a lot of commonality between what we're saying here and that what Ryota's saying in his models of intelligence and consciousness. I think there's a big kindred spirit there in what people at Raya are doing as well. So
thank you. And my final question is about recent hot topics by Google engineer of the very assay. Do you know the Lambda system? It's a conversational system. And one of the Google engineer said this Lambda system finally had a consciousness. So do you agree with that?
We humans are very good to anthropomorphize. When we see something that looks a little bit like us or sounds a little bit about us, to think that they really are like us. So I think that's part of what happened there. But the truth is, I think there is a sense that some of these machines, these deep learning machines, are building models of the world inside. They may have that, may have a little bit of consciousness now. And I think that one has to look inside the hood to see if there are these components. I think that it's not going to be the Turing type test to tell whether these machines are conscious, but it's going to really have a lot to do with looking under the hood to see what components they have and how things are put together. It's so this Lambda thing is very much like the Turing test. It's a thing to very easily to, I think, confuse or to make assumptions based on something that a writing that says, this computer will say, well, I am conscious. I am, or don't, I deserve, I think that machine was saying it deserves the salary. It had to be
Lenore, I don't know if it's worth continuing. I don't know how many people there are still around her.
Yeah, there's a number of people, so I think you should go on. Hiro, I think Manuel should go on with some of the questions. What do you think, the FAQs?
So
would people like to hear some of them? I think there's.
So and then maybe after that, Nicholas will have some questions.
Oh yeah, well, actually, let's get Nicholas. His hand's been up for a while. Nicholas,
fair enough.
See you? See you?
Well, I don't have a camera, so you're just going to get audio. Normally there'd be a picture of a cat or something, but I'm not logged in.
Okay.
I guess I'll be kind of, well, okay. So Lenore, in your talk, I kind of thought you were going for something, and then it sort of veered away, because a lot of the structures, you introduced the sort of idea of computational or feasibility in computation, and a lot of the structures in the model you presented are things you would do to optimize for certain concerns rather than necessarily things you have to do. Like, talking about this construction to make the tournament fair. If you just did an all-to-one thing, you wouldn't have to worry about this kind of intensity propagating forward to make it fair. But if you were thinking, I want the computation to be done in a way that's scalable and localizable.
Wait. Let me speak to that.
Okay.
Because I do get, look, so what you're suggesting is that for the competition tree, all you need is for each processor to know its probability, its weight, the total sum of the weights, its own weight, and now it knows with what probability should go up there.
Yeah.
But if you even want to get the sum of the weights, you need a tree to get there quickly.
Well, that's
and
what I'm
even
saying.
Once you've got that tree and you've got the sum of the weights, what do? You know a weight and you know the sum, so you know the probability with which you should go. But should you go with that? Should you toss a die to decide whether to go? Maybe nobody will actually win. Maybe several people will win. How do you actually, in the end, decide who's going to actually get up there?
Well, I guess that's what I'm saying. That let's say I don't care about efficiency and parallelization.
No, they're very important. That's
yeah, exactly. So what I thought,
you cannot have consciousness without that.
But so what I thought you were going for in the beginning was to say, all right, there are other models or other things that people do, but the computational limits are going to actually be really interesting. And so independent of whether we have the specific implementation that one would claim is or isn't conscious, we could say that there are some fundamental computational limitations of any conscious system using this to structure the topology that any kind of that anything that has a bottleneck of a small working memory and a large database from which that small working memory draws is going to have to pass through. So I thought, like, okay, you could make this really clever thing where you say, you could argue that our system is or isn't conscious, based on your own spirituality or whatever. But if you think that consciousness only processes a small number of things at a time, and it accesses a scalable backend, there must be this thing that we can say about the computational limits. That was kind of what.
But we don't. And that maybe you're interested in what Tononi does, but we are not doing that. We are.
Oh, I don't think it has to do with Tononi. I think Tononi's thing is totally separate.
And then arguing for it having for the possibility for it being having the properties of consciousness.
Yeah, I mean, I guess like in that sense, I would say, well, how does if I take away the specific computational, let's say the considerations about parallelization and scaling of parallelization, then you could look at something like an attentional neural network, and it has a lot of the features of your system, or it has, I think, all of the features of your system aside from the specific optimizations, in the sense that each piece of information in the larger memory is weighted. It's weighted based on a gist that is used to determine whether that enters into a central processing thing. And of course you can have, and people have done attention-based world models, but it seems like the thing that would be kind of like the knife edge that would separate those systems from this system would be if there are additional constraints from the need to be able to sort of extend your system dynamically, whereas those systems can't be extended dynamically because they have quadratically scaling memory requirements and other horrible things like that.
I think you're asking something from us which we're not wanting to give.
It could be. I guess I'm trying to suggest, like, from the broader the broader context of machine learning, there exist these other models that are very similar to yours. They're not the same as yours. The thing that is different is this particular consideration about the computational scalability. So it seems useful to see if that's doing any work. Like if that's actually, if that particular difference is letting you determine or predict something that those other models can't.
Well, that's a wonderful question, and I think that you should work on that. I'd be happy to hear from you.
Yeah, I think you're raising a really great question. Yeah, I think that's a really great question. And the question, as I see it, is there something really deep here in terms of our emphasizing resource limitations?
Mm-hmm.
So if you don't have the resource limitations, you know, so I think that's what sort of
It's much, for example, it's much harder to explain the feeling of free will that one has if computations are instant, if there's no time required to do it. Because when you're in the chess game and you're trying to decide what move to make, you don't know what move you're going to make until you've done those computations, and that takes time. And during the time that you're trying to figure it out, you know that once you figure it out, you'll decide. But you don't know what that's going to be.
Yeah, I mean, I think like that's really key, because there are all of these theories, like the free energy stuff, that kind of assumes this omnipotent computer behind them. And then it's sort of like, oh yeah, well, AI is done because you can write this and this is the optimal function and so on. But of course it's not because you can't do it. So I think like, I guess what I'm trying to say is like, the thing I got from your talk is there might be some extra constraint, which I don't think you explicitly actually stated, but would be really important, that would inform, say, all of these people doing things like the large language models like Lambda, which are attentional. They do have a kind of a working memory kind of structure to them. Like the perceiver has a small working memory and a large background memory and so on. And people are using these things and just using whatever they can kind of fit into their GPU of whatever size that they have. But if there's a scaling argument about why you have to use a tree, and why when you use a tree, it's going to put certain bottlenecks on the information and so on, that could be really important. Not just from a point of view of consciousness, but also from the cognitive point of view of what these systems can do. So like, that's what I'm kind of, I guess, picking up on, that there's something here that feels like an opportunity.
Yeah, thank you. But I think let's like dig deeper more today, like the Lenore Manuel's models, and like maybe we can come back, but let's like,
that's fine.
Let go through the FAQs.
Yeah, but before Manuel goes ahead, I would like to say, I think you brought up a good point, Nicholas, and I think that in fact there is probably a deep theorem looming here. And I think you're sort of pointing away to something that could be very, very deep here.
I agree.
Right. And as Manuel said, it would be great to work if you could work on it or point out more. But I actually think you're making a really great point here.
Okay, I'm going to go on to some more questions here. Maybe get through them quickly. Why is the resolution mechanism of the uptree competition the specific one that is proposed? Well, I think I explained that it's a specific one because every processor has a probability of getting up there. It's fair, and because you can permute the processors and not change what actually gets up to STM. Which, okay, so that's go on to the next one. Why do you focus on the probabilistic rather than the deterministic CTM? I'll just say that we wanted the deterministic CTM. We started with a deterministic CTM, but it required all kinds of special cases. We had to make all kinds of special rules. The whole machine became complicated to do stuff which the probabilistic one does automatically. The probabilistic one just ends up being much simpler. Should I give an example? Just as an example, well, no, let me keep on going. Why an uptree at all? Well, you have to get the information. You have to find out what information should you get up to STM. Why do the authors choose to have intensity and mood in the chunk? It seems equally valid to discard them. That's interesting. This question was asked by one of the reviewers who did not like the paper. Why do you have intensity and mood in the chunk? It seems equally valid to discard them. So theorem, if you don't have intensity and mood in the chunk, if the chunk is just Without that, you cannot have a fair tournament. You cannot. It's absolutely essential. It's a theorem. Where does feedback come from? Well, so Lenore sort of suggested it, what's her name, etc. How do processors judge how valuable their information is? It's very interesting. That's a question of how do processors get the weights that they choose. That's what the sleeping experts is about. The current papers on the sleeping experts don't completely answer the question, because in the sleeping experts paper, there's a teacher who knows the answer and is basically adjusting the weights of all the students in the class. This is in the CTM, there is no such teacher. There's each individual processor has its own a sleeping expert to adjust things, and to get that working is very interesting. Why would chunks contain queries and answers? Well, the query, what's her name? Answer, it's Tina or whatever. Must the CTM have a model of the world processor? Yeah, we think this is absolutely essential. We don't see how to make clear what's going on without a model of the world processor. Maybe I could say a little bit about this. Dreams. So, by the way, the same person who asked some of these questions also said, "Why are dreams so important to you?" So let me just mention, it's important here that why dreams come up. Dreams are really important because they are. Just think of it: a dream that you have no input, you have no output in your dream. Everything that you're seeing in your dream, everything you're hearing, everything you're sensing in the dream is completely created by your brain. It's just wonderful. And the model of the world processor is very important for this, for keeping track. Well, okay, so yeah, trying to get. Okay, isn't naming specific processors, such as the model of the world processor, indefinite and final terms and overspecification? There are many, we don't want to be over, we're giving an example. It is true. Our model of the world, the one that we eventually come to, is just an example, just like a universal Turing machine is an example of a Turing machine. It's nice to know that it can exist. It's nice to see how an example works. The same thing is true here with model of the world. Why would the whole cortex not constitute a model of the world processor? Absolutely, the whole cortex is a model of the world, but we have some special processors that really deal with that. And it's interesting that in the brain, you do have the hippocampus seems to be an important part of the brain that has the model of the world. When people look at the EEG of when people are looking at what the rat is doing in a dream, you can see the rat's been taught had been given a maze. It has to learn how to go through the maze to find the food. When it dreams, you can see that rat going through that maze. In the hippocampus, you can see it actually moving around to find its way around. So let's see. Okay, so that's okay. That's already. Should I keep on going, or where are we at here?
Almost done.
Yeah, if you don't mind, you can just go through, and we can have some questions from people's.
Okay, so I should keep on going. Question 19, why would the lack of input from the environment lead to incoherent thoughts and dreams? That's another question that came back from a reviewer. We're not saying that it has to lead to incoherent thoughts. We're just saying that if you don't have input from the environment, in a dream, you can, you know, how are dreams created? The dreams do have information that you get from the environment, but it's really important for a CTM to be able to predict what the effect of doing something will be. That, you know, if whatever it's doing, it's got to be constantly predicting exactly what's going to happen, and it's got to learn from that. If you don't have the environment, if you have no input, no output, as you have in a dream, you don't have an environment to tell you that you're going off in strange ways. So it's not that lack of input leads to incoherent, but it can lead to incoherent thought. It can lead to strange things. It can, you know, you can have a dream that you're flying. You've never been flying in your life, but you know, not like Superman, but you can do that in a dream because the model of the world has the apparatus to be able to do predicting. Okay. What question does the theory address that is not already accounted for by the standard global workspace theory? Let's see. Yeah, so I think the answer here is that this CTM is substrate independent. So the standard global workspace theory assumes that you've got neuron, you know, it's dealing with the real biological neurons. We don't have neurons in this whole thing, so we're looking at what you can do without having even if instead of biological stuff, you have just silicon and gold, and you can use gates. You can still develop this theory. Does the CTM have free will? I said a little bit about that. We say that no, the CTM and you don't have free will, but you do have the feeling that you have free will. When you have to make a move and you don't know what choice you're going to make because you have done the computations, you just know that well, you'll do the computations, you'll figure out what's the best move to make, and then you'll choose that. So you have the feeling that you have free will. Do you have an implementation of the CTM? We have Jean-Louis Villacroze is doing an implementation of the CTM. We have Paul Yang, as Lenore mentioned, who's working on Brainish. There have been some parts of the CTM have been implemented by students. Do we have an implementation? Not yet. We'd love to have it, but we don't have it yet. Why is there no mention of neural correlates of consciousness? Well, because we're not dealing with the brain, we're dealing with the CTM. Could brain dynamics and competition between attractors be a more neurally plausible explanation? Again, we're not trying to have a theory of the brain, we're trying to understand consciousness. And for that, we use the mathematics that we find most useful for us. Assuming the brain is a CTM, what are some conditions for a part of the brain to be considered the short-term memory? So that's sort of the short-term memory, you know, if it's the top of a tree, it doesn't have to have very many inputs, but the output has to go to it has to have this huge broadcasting system. It's got to be able to broadcast to all processes at the same time. So these sorts of conditions have been considered, and I know that Coach has thought that has suggested some parts of the brain that might have this property.
Claustrum,
yes. Thank you. How are ideas to be checked? You know, this is important because math uses proof to check ideas. That's wonderful. Physics uses experiment, physics, biology, chemistry. They use experiment to check ideas. It's wonderful. How is one to check if the arguments of CTM theory are correct? Wow, that's a very important question, and I don't have a good answer. We don't have, we've started to give some arguments, but we don't have a general, we have not yet figured out what would generally work. Let's see, almost done here. What are some examples of what the theory explains and what it does not explain? Yeah, a whole list of things here. Okay, I'm going to tell. What are some examples of what the theory explains and what it does not explain? So what it explains is, like, why make short-term memory so small? People who are thinking of simulating this always say, well, you know, why not make the short-term memory large? If memory is cheap, you could have something very big, but then you would lose the focus. So why is it so small? Because you want focus. How is the CTM defined? How are chunks defined? You know, chunks were first defined by George Miller, but they weren't definitions. They were just ideas. At least in the CTM, you can, because it's a mathematical theory, you can define a chunk precisely. How do processors define weight? What makes being so realistic? A bunch of questions. Let me get to the ones that okay, so let me get to unexplained phenomena. So here's one that I like. You know the Hebbian principle, neurons that fire together, wire together. Oh, I love that. It's beautiful. But what about, what do you say is the Hebbian principle in the CTM? It kind of gets you thinking about it. First of all, there are no neurons in the CTM, or they don't have to be. They could be, but they don't have to be neurons in the CTM. So what does it mean? Neuron that fire together, wire together. If you think about it in the case of the CTM, you see that he's really talking about inputs that occur at the same time. I mean, there are, after all, neurons throughout the brain that are firing at the same time. They're not getting wired because they're firing at the same time. No, it has to do with inputs. You get an input from the eyes that says lightning. You get an input from the ears that says thunder. They're occurring closely enough together that you want those two processors to be linked. So what is the Hebbian principle? I would like, I don't know that how, you know, I would love to be able to define the Hebbian principle precisely. What else? Is it wise to give the CTM architecture? Okay, this is the last one, so I'll take time. Is it wise to give the CTM architecture to our computers and robots? Put another way, is it wise to make our machines, or at least some of our machines, conscious? Is it wise to make them conscious? A very wonderful question, I think. And it reminds me, do you remember, you know, the Council of Elders? You know, the chimpanzees, some time ago, were they were fighting amongst each other, and so their Council of Elders got together to try to decide what to do about this. All the chimpanzees fighting. Let's try to do something intelligent to stop this. So one suggestion was, let's have these, let's bring in love more. Let's make a chimpanzee where love is all important. And in fact, there is such a chimpanzee. It's what's the name of it, Lenore? The
Bonobos.
Bonobos, yes, wonderful. It was very successful. The bonobos don't fight. When they have a problem, they have sex. and that takes care of it. I love it. There was another suggestion that the Council of Elders made among the chimpanzees. Let's make a more intelligent chimpanzees. Let's have we'll call it a Homo sapien. It'll have a big brain. It'll be intelligent enough to get us out of all the problems that we have with each other. Do you think that'll work? I think the question, it's still a question whether that's a good way to go. Anyway, that's the end of this lecture. We do want to acknowledge the support. What did I do here? I'm having trouble because of okay. So we do want to acknowledge the support of Michael Schwann and UniDT, which is supporting this work. And thank you very much.